Welcome viewers. In this video we'll see the Maxwell's equation. There are four equations available in both integral and differential form. First we'll see the first Maxwell's equation, that is from Ampere's law. First Maxwell's equation is obtained from Ampere's law. So according to Ampere's law, the line integral of magnetic field intensity H around a closed path is equal to current enclosed. It is integral H dot dl equal to I. So that is the statement given by Ampere's law. In general case, we consider the total current involving both conduction current and displacement current. Here we are considering both conduction current and displacement current. Conduction current means current flowing through normal conductor with resistance R and applied voltage V. Displacement current is nothing but current flowing through the capacitor. The current flowing through the capacitor is termed as displacement current. Here we are considering both conduction current as well as displacement current. So integral H dot dl equal to double integral J dot n cap ds, that is equal to I. So integral H dot d equal to I. In terms of current density is given, double integral J dot n cap ds. But J equal to sigma E plus dou d by dou t, the current density in other form. Now we can replace this J with this expression. So integral H dot dl equal to double integral sigma E plus dou d by dou t into n cap dot n cap ds. If the medium is free space, that is, we can replace d equal to epsilon E. Right? The d available here can be replaced as epsilon into E. So that integral H dot dl equal to sigma E plus epsilon dE by dt. d by dt is now replaced with dE by dt into n cap ds. Right? That can be splitted into two. We can split into two terms. Integral H dot dl equal to double integral sigma E dot n cap ds. That is, these two are multiplied. Now these two are multiplied. Epsilon dou E by dou t into n cap ds. Right? So the first term is referred as a conduction current. The second term is referred as a displacement current. You take this is equation number 1. Right? So finally we can write integral H dot dl equal to double integral curl H dot n cap ds. This term can be replaced as curl into H. Right? So this is nothing but the Maxwell's first equation in integral form. Integral H dot dl equal to double integral curl H dot n cap ds is the Maxwell's first equation in a integral form. Now we'll see the differential form. So according to Stokes' theorem, this integral H dot dl can be written as double integral curl H dot n cap ds. Right? So according to Stokes' theorem, it is written like this. We take this equation number 2. So by comparing equation 1 and 2, this left hand side is equal, integral H dot dl. So that we can equate the the terms available in right hand side. So that curl H equal to sigma E plus epsilon dou E by dou t. That is available in equation 1. So this curl H is written as del into H, that is equal to sigma E plus epsilon dE by dt. Right? So this equation is nothing but Maxwell's first equation in differential form. Previous one is the integral form. This is the differential form. Right? So now we got the Maxwell's first equation from Ampere's law, both in integral form as well as differential form. Now we'll go to the second Maxwell's equation. The second equation is from the Faraday's law. What is Faraday's law? Faraday's law states that the voltage induced around a closed path is given by negative of time rate of change of magnetic flux in the path minus dou by dou t of pi, rate of change of flux in a decreasing order. That is given by Faraday's law. EMF equal to minus dou by dou t of pi. Now we'll see the flux density B equal to pi by A. So by cross multiply this, so pi equal to B into A. So that can be written as phi equal to double integral b dot n cap ds. Now we'll replace this pi with this expression. From equation 1, this pi is now replaced with this expression. So the equation 1 become EMF equal to minus dou by dou t of double integral b dot n cap ds. So that it can be written as integral E dot dl. The EMF also expressed in terms of integral is E dot dl. That is equal to, multiply this inside, minus double integral dou b by dou t dot n cap ds. Right? So integral dl, integral E dot dl equal to minus integral double integral dou b by dou t dot n cap ds. So this is nothing but Maxwell's second equation in integral form. In a integral form, that is from the Faraday's law. Now we'll see the differential form. So by referring the Stokes theorem, integral E dot dl equal to integral del cross E dot n cap ds. The expression given by Stokes theorem is double integral E dot dl equal to integral del cross E dot n cap ds. So from equation 1 and 2, this left hand side is equal, so we can equate the term in the right hand side. Right? That is del cross E equal to minus dou b by dou t. By equating the right hand side term in equation 1 and 2, we got this. So this is nothing but Maxwell's second equation in differential form. Now we got the Maxwell's second equation in integral as well as differential form. Now we'll go to the third and fourth equation. So third and fourth equation from the Gauss law. What is Gauss law? According to Gauss law, flux coming out of a charged body is equal to the amount of charge enclosed. Pi equal to Q. Flux coming out of a charged body is equal to amount of charge enclosed in the circuit. Now we'll see what is pi, what is Q. So from displacement density is given as d equal to d pi by ds. And cross multiply this, d pi equal to d dot ds. So by pi equal to, by integrating on both sides, pi equal to double integral d dot ds. Right? Now we got the expression for pi from the displacement density. Similarly, by referring the volume charge density rho, dq by dv. Volume charge means charge per unit volume. You cross multiply this, dq equal to rho into dv. So by integrating on the both side, q equal to triple integral rho dot dv. Because of volume, we are having triple integral. Right? Now we got the expression for pi and q. So that can be substituted in the equation 1. Pi can be replaced by this term, q can be replaced by this term. Right? So the equation 1 now become double integral d dot ds, this one, equal to triple integral rho dot dv. Right? This is nothing but Maxwell's third equation in the electric field, in terms of electric field. Similarly, we have magnetic field available. So this is the Maxwell's third equation in electric field in integral form. The same thing from the divergence theorem. It can be written as del dot d equal to rho. By referring the previous equation from the divergence theorem, we can write like this. So this is nothing but Maxwell's third equation in electric field in a differential form. The third equation for electric field in differential form. This one is integral form, this one is differential form. Now we'll go to the fourth equation in magnetic field. Suppose in case of magnetic field, the surface integral of magnetic flux density B over a closed surface is S is 0. That is double integral B dot n cap ds equal to 0. That is given by the Gauss law in for a magnetic field. So this is nothing but Maxwell's fourth equation for magnetic field in integral form. So the same equation can be written as del dot B equal to 0. So this is nothing but Maxwell's fourth equation in of magnetic field in differential form. Right? Now we got the all four Maxwell's equation both in integral form and differential form. So in this video we discuss about the Maxwell's equation, right? 4 different equations available, both in integral form and differential forms are discussed. Thank you.